This is an ordinary trolley, and I have the pleasure of kneeling on it. Both the trolley and I are at rest. There's no motor, so how might I get moving without touching the wheels or getting off? Well, I happen to have this heavy ball. What will happen if I throw it away from me? Here goes. The engine that propelled me was the law of conservation of momentum. To begin with, I had no momentum, and neither did the ball or trolley. By throwing away the ball, I gave it some momentum p in a particular direction. But by doing that, I gave myself and the trolley a momentum of the same magnitude, but in the opposite direction, because the total momentum of the system must still be zero, just as it was when I was stationary. Let's investigate the law of conservation of momentum under controlled conditions. Here is a horizontal pair of rails. You'll see several gliders like this, which operate on a cushion of air. Let's take the lid off and have a look inside. Air comes in through a thin tube and is directed to the four corners of the base. It's then forced out through holes on the base, here, here, and two more on the other side, so that when it sits on the track, it floats on a cushion of air, and even the slightest push results in movement. You're going to see gliders like this colliding with each other in a number of ways. Sometimes you will be asked to time how long it takes a glider to travel a fixed distance of 40 centimetres before or after a collision to get a measure of its velocity. To give gliders a controlled initial velocity, there's a spring mechanism controlled by remote electronics. This will be used, at least in the first two experiments you'll see, to provide the system with identical starting conditions. On the front is a spring, which when compressed will propel the hovering glider away. In the middle of this spring there's an electromagnet which is attracted to a metal plate on the yellow glider. When I bring them together, they stick and it's ready for firing. Let's see what happens when we turn the electromagnet off. In the experiments that follow, you'll see gliders like this, and they've all been fitted with pointers to mark the position on the fixed scale. In this apparatus, it can be arranged for one glider to be fitted with a spring. The two gliders will meet and bounce apart. Since no kinetic energy is lost in this collision, it's elastic. On the other hand, here's a simple coupling mechanism, a friction shaft which engages into a hole on the other glider. When the gliders stick together like this, the collision is inelastic. Okay, let's begin the experiments. First of all, there's the case where one glider is stationary. In this first experiment, there will be an inelastic collision between two gliders of equal mass. The orange glider is ready to be fired off, and the yellow glider is hovering at rest. Can you predict what will happen when the orange one is released? Well, the two gliders move along together, but by how much has the velocity dropped? On the other hand, if you arrange for the same two gliders to collide elastically, what do you expect to happen? It would appear that they just swapped their velocities, with the orange glider stopping and the yellow glider moving on. You're going to see these two experiments again, but now the times will be displayed at which the pointers reach the start and end of each distance marker. This is the inelastic collision again. And here's the elastic collision once more. Knowing also the mass of the gliders and the fixed distances, you're now in a position to calculate some momenta and energies. Calculations of changes in momenta show that momentum is conserved in both types of collision, at least within an experimental error of 5 to 10%. In terms of changes in kinetic energy, though, the inelastic collision experiences losses mainly due to friction, whereas the elastic collision in fact conserves kinetic energy. Next, you are going to see those same gliders moving towards each other at similar speeds and colliding. This time, just observe qualitatively. Firstly, the inelastic collision. Well, the two gliders stopped dead. What does that say about the change in energy? Well, it hasn't disappeared. It's all been transformed into both frictional and sound energy. Here's the elastic collision now. How would you expect momenta to change after this type of collision? Since they then travel in opposite directions, they would appear to swap momenta. What's particularly interesting is the behaviour of the two gliders when they are both travelling in the same direction. Once again, the gliders will start by making an inelastic collision. You will be seeing that inelastic collision again as a quantitative experiment, but before that, here's the elastic collision. Let's rerun both experiments, but this time provide you with quantitative timings. The inelastic collision again. And the elastic collision. These are the sets of data which apply to gliders travelling in the same direction. You can now check whether the conservation laws apply in these two cases. As before, calculations can confirm that momentum was conserved in both collisions and kinetic energy was lost only in the inelastic collision. The inelastic coupling itself was where kinetic energy was lost, but thereafter the joined gliders shared a velocity. This was somewhere between the velocity of each individual glider. The elastic collision led, as always, to an exchange in velocities with effectively no decrease in kinetic energy. But coming back to this trolley, it obviously took some kind of force to get me moving. But where did it come from? Did it come from pushing the ball against the air? No, it's arisen simply from the conservation of total momentum, created independently of the medium I'm in. Indeed, no medium is needed for this propulsion mechanism to work. For example, this astronaut is wearing an MMU, Manned Maneuvering Unit. For any change of motion, small quantities of gas are thrust into empty space, and he gets to move with a change of momentum equal and opposite to the momentum of the ejected gas. In fact, he's being propelled by ejecting relatively tiny amounts of mass. You can see this principle in action on the air track. This time, the glider is going to be forced along by ejecting small masses like this swan. Small, that is, compared to the mass of the glider itself. There are 3 of these, 2 are in place, so let's put the third one on. Let's see what happens when these 3 masses are ejected one after the other. Taking a closer look at the velocity changes, a quantitative experiment would show that the acceleration produced by each firing is practically the same each time. Similarly, each firing of the MMU will result in the same acceleration as long as the loss of mass of burnt fuel is negligible against the mass of the propelled load, that's the astronaut and the MMU. Each time he fires his jetpack, he changes his momentum and therefore accelerates. The constant acceleration which this glider received relied on the fact that the ejected masses which forced it along were so small that the overall mass was fairly constant. So the acceleration can be found from Newton's second law. A is equal to F divided by m. Let's modify the experiment. Here's the main glider, but this time we're going to propel it by firing smaller gliders whose mass is comparable to that of the main one. There are 3 of these. 1, 2, 3. What do you think will happen to the acceleration of the main glider as each of the stages is fired? Each time the next stage was fired, the acceleration was greater, although the acting force was the same, that is, identical springs. Why? And it's because the mass being propelled got smaller and smaller when each propelling stage was lost. So Newton's law still holds true, but it can only be applied through each limited period over which the mass remains constant.
3, 2, 1. We have ignition, we have liftoff.
A similar thing happens when you need to burn a large amount of fuel to get a large mass into space.
It's in controlling now.
But of course, this time, the mass is decreasing continuously, and so you can't describe the motion using the simple form of Newton's second law, force equals mass times acceleration. But you can still describe this motion if you think in terms of the rate of change of momentum.